and I am creating a new project which is HFSS design 1. In this case, this is an array antenna here. Okay, so in this particular array creation, I need to go for two things here. One will be my boundary condition change, where open has to be deleted and I need to change it to lattice pair. And the second one is I need to attach the radiation box or the boundary box. I can say it as boundary region along X and Y. It should be attached to the substrate. Like this gap, it should not be there. The gap from here to here along X and Y, it should not be there. It has to be attached to the substrate, so that in a single substrate only we will be repeating the elements. So these are the two things we are going to edit, or else you can just delete this radiation box, create a new box. Okay, so let's suppose once we had done with this, the first thing what I said was I'll just delete this open region boundary condition. So I had deleted this. Then the next thing is I need to change the gap here. So for changing that particular gap, you can already the radiation box which has been created, you can just go and edit this. So you can see here, once you click on create region, along X and Y make it as 0. This 3.73 you can just along a plus X and minus X 0, plus Y and minus Y again 0. Click on apply and OK. You can see this particular, it has been attached here. The gap which was there, it has been reduced here. So the next condition is we need to assign lattice pair boundary condition along X and Y, where my lattice pair will, what it will be doing here is it will be replicating the structures. Okay, and my along Z axis it is the radiation region, along Z axis it is the radiation which is happening. So I will fix the radiation boundary condition along Z axis. So the first thing is we need to assign lattice pair boundary condition along X and Y. For that, go to select, choose the phases. We will be choosing opposite phases, then only the lattice pair boundary condition will be applied. How in master slave we have to choose perpendicular boundary perpendicular phases, the same way we have to choose an opposite phases here. So first I will select the positive X, just I will rotate this, and using control I will select the second phase, the opposite phase here. Right click, go to assign boundary. In lattice, in couples, you will be finding lattice pair here. So just click on lattice pair. It will ask for name. Just click on next, and then it will ask for the phi and theta values. This phi and theta values is nothing but in which particular polarization angle my signal is going to come and hit my signal, that is my radiations. For example, if I keep this as antenna as an base station antenna. Okay, so in this particular part, let's suppose I am going to along this particular X axis I am keeping. Okay, so this phase in which particular theta and phi. Theta is nothing but my elevation angle. So along height, this particular angle, how in which direction it is coming, and along this particular horizontal rotating angle, in which particular direction. Based on that, how it will be coming and impinging. So this is basically nothing but, here in this case, it's in which particular angle my mobile signal will be coming and hitting. Because of that, how my beam forming will be, or beam steering will be happening. So to calculate that, we will be giving this as phi underscore scan. Just we will define a variable here, which is phi underscore scan, and for theta we will give it as theta underscore scan. Then finish it. It will ask for what is the value of that particular variable phi underscore scan. Initially keep it as 0 degree, and theta underscore scan the same 0 degree. So initially we are not giving any value here, just we are giving it as 0. Then the same way along Y we are going to select two phases here. So along X phase we had assigned phi and theta, in which particular angle for an 5G beam forming we will be getting it. The same way we will be assigning lattice pair along Y axis now. again right click, go to assign boundary, coupled and lattice pair here. So this will be lattice pair 2. Next, again it has been defaultly taken from the earlier input. So click on finish. Now lattice pair 2 boundary condition. Lattice pair 1 is along x axis and lattice pair 2 is along y axis. Next, choose the radiation boundary condition here. Choose z axis, positive and negative z. Go for assign boundary, then just give radiation here. Then click on OK. Now your antenna, whatever you had made for a single element, now it represents an unit cell, infinite number of elements it will be representing if we didn't give any kind of input to the lattice pair. It is kind of an infinite number of cells array which we had created. So just to define the number of elements, how many number, but it is not practically possible. So
we can use fluctuate port here. Like, what's the difference between fluctuate and
fluctuate port, when we will be using the port is like when we go for unit cell analysis. Let's suppose why we are going for fluctuate port is you will be having a kind of structure here. Okay, unit cell analysis. Like I am going to pass a wave from this end to this end. How in a transmission line. So this is my transmitting port and this is my receiving port. Okay, but what we are going to see here is in this particular angle, why we will be going for fluctuate port is in each and particular angle of phase of inputs. Okay, in in a plane wave excitation, let's suppose we can define this unit cell analysis in another way also. How it will be in the sense, you can let's suppose this is duster available. So let's suppose this is the box kind of structure which we are making and this is the element in between which we are keeping. So the two opposite faces, it will be perfect T.
master and
One will be master. Before master and slave also, without using fluctuate port, if you want to go with wave port or lumped port. Okay, what it will do is we can use perfect T on one face and perfect H on other two faces.
Yes.
So if you excite a wave here, using a wave port, if you excite it like a kind of a waveguide structure, what it will do is my electric field components will be absorbed by perfect T. My magnetic field components will be absorbed by perfect H. So only the wave propagation will be in a single direction. Whatever the wave I am impinging from this end to this end, because of the material property, it will be disturbed my phase, because let's suppose it is a kind of an EBG structure.
okay.
Electromagnetic bandgap structure. So these structures will stop the wave at that particular frequency and it will be a kind of a stop band response we will be getting. So the same kind of analysis we are doing in unit cell. When we go for an unit cell analysis, instead of giving the particular PE conditions, we are going for master slave or lattice pair. And why the advantages of master and slave and lattice pair is like we can go for define in which particular angle the incident wave is.
So we can define using the theta and the scan values.
Scan values we can define, and the same kind of input which we are getting, in which particular angle my wave is going to come and impinge. Is it a perpendicular to this or in this particular angle? That we will be defining in fluctuate port.
But here we are not defining that electric and magnetic boundaries.
No, it will automatically take observe that, but because we are not using this, it will be suppressed like the wave phenomena how is going to impinge there.
Okay.
So in this case is like why it's not fluctuate port is like in unit cell what we will be doing is the main concept I forgot actually. The thing what we will be doing in unit cell is we will observe what kind of material characteristics or what kind of how this particular structure we are making, it will be behaving to the plane wave or any kind of wave which we are impinging. Okay, electromagnetic wave. But in case of antenna, how it is in the sense, this will be radiating out. This is the source which I am generating. Okay, but in other cases like the source will be generated from here and it will be absorbed, and based on this particular material how it reacts, that is what we will be seeing. So this kind of phenomena where we will go is meta surfaces or those kind of scenarios we will go there. So what we will do here is we will just select a particular structure, we will make that unit cell. That unit cell, what we will do, we will say like this is creating an stop band at 2.4, or let's suppose pass band at 2.4 gigahertz. Okay. So what it will do is, we will make an array of meta surface over, like superstrate we will make over this. So this excited field, whatever the radiated field it is coming, that will excite the metamaterial structure or the meta surfaces, whatever we had made.
Okay.
The wave which we are trying to impinge here is nothing but the clockwork port is generating a wave, no? That is the wave which has been generated by my antenna. We need to make an array of structures into this. So for making array, just right click. You can see once you use lattice pair boundary condition, automatically domain decomposition method solver will be. Right click on create array option. Here it will ask for lattice pair. In along lattice pair 1, how many number of structures needs to be created, and along lattice pair 2, how many it should be. So you can change the numbers here. Just we'll go with let's suppose for simplicity case I will go with 4 cross 4. This itself will take too much of time to get simulated.
2 cross 2 is fine.
Yeah. Also thinking the same.
1 cross 1 is better.
It is
No
the same.
array.
No, no,
Quite
2 cross
difficult.
3 you take, sir. 2 cross 3 you take.
2 cross 3.
Just I will reduce the sweep and this thing. Let it be 5 cross 5 itself.
No, 2 cross 3.
No. Competition time I will reduce, not an issue.
No, 4 class 4. 4 class
Let
5.
it be, sir.
Okay.
No, exactly.
Okay, Shankar. We change
Okay.
for our case.
So, 5 cross 5, 25 elements has been created here. Okay, the simple change I am going to make it out here is, first thing is excitation. I have to excite all the structures. Just without the beamforming application or the using toolkit, we'll just go ahead. We'll go to edit source. Just I'll change it to the input to be 1 volt to all. We'll see if I excite all the systems, is my gain is improving or not. So I'll apply and click OK. Just for simplicity case, to reduce simulation time, I'm not going for frequency sweep. I'm just set up.
Change the frequency.
I'll convergence also I'll reduce it. Anyhow, if I reduce convergence, that doesn't matter with this thing. 0.1 I am keeping it. So maximum course I use here. So we'll run the simulation.
So that we have to go with HPC option, sir.
Yeah.